Hello, my name is Todd Rothman, and welcome back to Organic Chemistry 1. In this video, we're going to cover acids and bases. Now, you might be wondering, why are we doing acids and bases when you learned all about that in Gen Chem 1? Well, the thing is that we're going to start by learning some of the details that we did learn back in Gen Chem 1, but we're going to quickly move in a different direction. You see, in Gen Chem, when you learned about acids and bases, you learned things in a quantitative point of view. You had to calculate pKa's or pH values, and you had to figure out how to interpret that information to decide whether a reaction is favored at equilibrium, for example. So primarily what you did in Gen Chem was work with the information about acids and bases from an analytical, or I should say a numerical point of view. In organic chemistry, we're not going to focus so much on calculations. You could throw out your calculator. You don't need it for organic chemistry. What we're going to do is we're going to use the information of the structure, and we will use the information provided from a calculation to determine more about whether a molecule can act as an acid or a base, okay, and how good it would be at that job. So what we're going to see is that in organic chemistry, we focus more on the structural information of a molecule and how that maps onto its acid-base characteristics. And so that's a very big difference. If you recall, in Gen Chem, you really never looked much into the structure of the molecule. You just worked with numbers, right? So you figured out things related that numbers can provide for you. So, like I said, very quantitative. In this case, we're going to do more of a qualitative analysis, okay? And you'll see what I mean as we go forward. So let's get started. The first thing we want to do here is we want to talk about, as always, a general definition of what an acid or a base is. And there are three that we're going to discuss, one out of respect, and the other two are actually very important for our studies. So what I mean by out of respect, so for example, when we look at Arrhenius, the first definition, we don't really use this definition anymore. It was very limited into what we can actually get from this definition, but we do respect Arrhenius, and so we always start by describing a little bit about what he thought. And you have to remember, this is 1887, right? So there's not much tools back then, and so, you know, he did a great job considering the limitations that he had around him. Anyway, so what did Arrhenius say? Well, one of the things that Arrhenius focused on was he focused on acids and bases inside water. And that was a major limitation to his definition. Okay? Because we know acids and bases don't have to only take place in water. And so that's why Arrhenius' definition was very limited. So what he said was that any substance that's going to produce H+, which is a proton. So any substance that produces a proton is considered an acid. And so what that actually includes are things like, let's say, HCl or sulfuric acid, H2SO4. These are substances that will, in water, right, this has to be in water, they will produce protons. Now, water is going to want to picking up that proton, but if we look at it, it will release a proton from hydrochloric acid. So we'll get that plus Cl minus, or H plus and HSO4 minus. So notice that these two are examples of substances that produce protons. So these are acids. Now, for bases, Arrhenius had a very limited definition. So again, remember, this is in water. So what do you see in water as a base? Hydroxide. So his definition was that anything that creates hydroxides is considered a base. So for example, if we have sodium hydroxide, that would be considered a base, because when this breaks apart or it dissociates, you wind up getting sodium and hydroxide. And so any of these group 1 metals in our periodic table would be considered, if it's coupled with a hydroxide, would be considered an Arrhenius base. But notice the limitation here, right? Arrhenius base is strictly hydroxide. That's not very good, right? But again, this is 1887. So now we go a little bit further up in time, and we have 1923, and now two scientists, both simultaneously but independent of each other, came up with a better definition or a better theory on what acid and base is. And what Bronsted-Lowry said was that an acid is anything that donates a proton. Okay, so with this respect, the Arrhenius is the same as Bronsted-Lowry. It's a proton provider, proton donor. But notice that this does not have to be in water. Up here, I said it has to be in water, dissolved in water. Here, it doesn't have to be in water. It could be in any solution. It could even be in the gas phase. So, very big difference, right? It's the same type of definition, proton, but it's different in the sense that it could be in any environment. Okay, so of course, Arrhenius's two acids I show up here can also apply to Bronsted-Lowry. So Bronsted-Lowry isn't going to replace completely. It's just building upon Arrhenius's definition. And so anything that's an Arrhenius acid is also going to be considered a Bronsted-Lowry acid, right? And so we can have things like H3O plus. We can have HCl, like I wrote up there, H2SO4, and these will all provide protons. And so they're acids. Now, a base is one that accepts a proton. Big difference, right? This is a major difference from the top definition. Arrhenius, we said hydroxide is our focus, whereas now we're saying, no, forget about hydroxide. Sure, that's a base, but what about other things that can accept protons? And that's what Bronsted-Lowry defined. They said that anything, so hydroxide, of course, can accept a proton, so it's a base, OH minus. But also, let's say NH2 minus or even NH3, as long as they're willing to accept some proton from the environment. So this becomes NH3, this becomes NH4 plus. So these are examples that are not hydroxides, but they accept protons, right? And so I could even go into carbon. A carbon that's negative can accept a proton. And so it's also considered a base. So anything that accepts protons. And so Bronsted-Lowry, if you notice, there's a large gap of time between the two, right? It's about 40-year difference for when Bronsted-Lowry came out to Arrhenius's definitions and expanded it, right? So you see here that Arrhenius, at the time, very limited in resources. This is the best that they can come up with. Well, Bronsted-Lowry was really good, but Lewis came up with the ultimate definition. So in 1938, Lewis came up with a better definition because he focused slightly different on the problem. See, and this is huge for organic chemistry because organic chemistry is all about where he focused his attention, and that is on the electrons. So Lewis said, you know, we're looking at it from a proton point of view, a proton acceptor and a proton donor, acceptor being the base, donor being the acid. But why don't we look at it from the point of view of electrons? Where are the electrons and where are they going? That's what Lewis contributed to this model. So he expanded the definition. He's going to include everything that Bronsted-Lowry has to say, but even add more to the story. So let's take a look. So an acid is the one that's going to accept electrons from a base who's going to donate electrons. So acids accept electrons, bases donate electrons. And that's what we're going to see here. So anything, like I said, so for example, let's say I have hydroxide and I treat it in H3O, so it's in an acid environment. Okay, well, then hydroxide will accept and become water. Let me not use H3O. I don't want to do this. So let's use HCl. So hydroxide will accept the proton, right? So notice that I'm saying this from a Bronsted-Lowry point of view, whereas the proton is provided by HCl, and so we get these two here, right? And so from a Bronsted-Lowry definition, we would say that this here is the base because it's going to accept a proton from this acid, right? And we could also do the same here. We could say that Lewis is going to look at the electrons. Notice that oxygen is negative, so that means that oxygen has 3 lone pairs. And if one of those lone pairs gives electrons to the H plus from HCl, then it's donating electrons. So from Lewis...